Welcome to the Explainer. Now, if you're here, I know you already know your way around a database. But today we are taking a definitive deep dive journey through advanced PostgreSql. We're looking at the complete query-to-system pipeline. That means we're going to start right at the foundation, writing highly advanced, optimized queries, and then scale all the way up to the overall database architecture and system-level performance. So get ready, because we are absolutely going to elevate your PostgreSql expertise today.
Okay, let's dive into this map. Here are the 5 masterclass topics we're going to cover. First, analytical window functions. Second, declarative recursive CTEs for hierarchical data. Third, high-impact indexing strategies. Fourth, we'll get into the math behind keyset pagination. And finally, we'll wrap up at the infrastructure level with connection pooling. Let's get to it.
Section 1. Analytical window functions. Complex calculations without collapsing rows.
If you have ever banged your head against a wall struggling with complex data aggregations, specifically where you desperately needed to keep the identity of your individual rows, well, this is your solution. A window function computes calculations across a defined set of rows, or a window, that relates to the current row. But here is the absolutely crucial distinction. It maintains individual row identity without collapsing the output. Think about your standard aggregate functions for a second, like a basic group by. When you use those, your rows are grouped and merged into a single output row, right? Window functions are entirely different. Each row remains completely separate, but the function still gets full access to data beyond just that single row.
So what does a window function actually look like under the hood? Well, it always relies on the over clause to create that window frame. Within that clause, you use partition by to define the criteria for grouping your records and order by to determine their sequence. But what you really need to keep in mind here is the execution hierarchy. Window functions are processed in the very final phases of the SQL execution lifecycle. They run after your join, where, and group by clauses. And because they execute so incredibly late in the query block, you physically cannot use a window computation directly inside a where or group by clause. It just won't work. Instead, you'd have to use a common table expression or a subquery to filter those computed outputs.
Now, to get even more granular with these, we use the rows between syntax to define exact framing bounds relative to our current row. You can set your window from unbounded preceding, which just means all the rows before the current one, down to a specific number of preceding rows. You can narrow it to just the current row itself, or you can look ahead with following rows all the way up to unbounded following. It's fantastic because this gives you ultimate precision over exactly what data gets included in your calculation.
Moving down the pipeline to Section 2, Declarative Recursive CTEs, Navigating Hierarchical Data.
Now, what's really fascinating about this next concept is how it fundamentally replaces your application code. If you've got a tree structure, think an organizational chart, a bill of materials, category trees, that sort of thing, traditional SQL really struggles. Often what developers will do is load all that data into the application and run a highly resource-intensive loop right in their code. Recursive Common Table Expressions, or CTEs, completely change the game here. They shift that tree traversal entirely into the database as an optimized declarative operation. The performance benefit you get from this is massive. You preserve your transaction consistency, you completely sidestep the verbosity of procedural loops, and you drastically reduce those expensive network round trips.
To truly understand why a recursive CTE is so efficient, we have to look at its physical execution model. It relies on a concept called fixed-point semantics, and it happens in 3 distinct steps. First up, the anchor member. This is invoked exactly once to establish your base case, like, say, finding the top-level CEO in an org chart. Second is the recursive member, which essentially acts as an active processing buffer, or your working set. This gets invoked repeatedly on the output of the previous run. And finally, the accumulator. This simply appends each successive output to a growing result set. The database just keeps looping that recursive member until it produces an empty relation, and boom, it returns your fully traversed tree.
All right, Section 3, High-Impact Indexing Strategies, the Execution Plan.
Look, writing a great query is really only half the battle, right? The database still actually has to execute it. And indexing is universally the single most impactful performance tuning technique available to you. 1,000 times. Let that sink in. That is the typical performance gain of adding a missing index. It is literally the difference between walking across the country and taking a supersonic jet. If you have an unindexed million-row table, a query might take 8 full seconds to run because the engine has to scan every single row. But apply the correct index, that exact same query drops to under 10 milliseconds.
But you know, not all indexes are created equal.
Here are the critical tools you need in your toolkit. The B tree is your standard everyday workhorse for equality, ranges, and sorting. But the real magic for read-heavy OLTP workloads? That happens with composite and covering indexes. A composite index uses multiple columns, but you have to remember it strictly follows the leftmost prefix rule, meaning your column order matters immensely. A covering index is amazing because it includes all the columns a query needs right inside the index itself. That means the database engine never even has to touch the main table, which effectively eliminates main table I/O. And finally, partial indexes. These let you filter high selectivity subsets, like, for instance, indexing only the orders where the status is pending.
On to Section 4. Keyset pagination over offset, stopping linear degradation.
So, what happens when you need to paginate really massive data sets? Well, if you rely on traditional limit and offset commands, you are creating a massive performance bottleneck at scale, and the math explains exactly why. Offset pagination degrades linearly. That's O of n. If you request offset 1 million, limit 20, the database physically has to scan, parse, and evaluate all 1 million leading rows, only to throw them in the trash and hand you the final 20. It's exactly like finding a page in a book by counting every single page from the very beginning every single time. It's incredibly wasteful. And worse, if data gets inserted or deleted while you're doing this, your rows are going to be duplicated or skipped entirely. Keyset pagination, on the other hand, also known as cursor-based pagination, uses a seek-based model. It operates at a beautiful O of log n. It acts like a highly precise bookmark, recording the last seen row's values as a deterministic coordinate and navigating directly to the next page. This guarantees completely consistent execution times and makes it totally immune to data drift.
But here's the catch. Keyset pagination doesn't just work by magic. To actually achieve that sweet, consistent O of log n performance, you absolutely must apply the indexing strategies we literally just talked about. Your database requires a composite index that perfectly aligns with both the cursor columns and the sort directions of your query. Without that specific matching index, you are going to lose all of those performance advantages.
Finally, Section 5, Scaling with Connection Pooling, Infrastructure Level.
Okay, so you've fully optimized your queries, your CTEs, your indexes, and your pagination. Incredible. But what happens when thousands of concurrent users hit your system at the exact same moment? 5 to 10 megabytes, that is the amount of server memory PostgreSql allocates for every single active connection. Database connections are really expensive. They require authentication, session initialization, and a solid chunk of memory. If you just have 100 connections sitting there, you're consuming up to a gigabyte of memory before a single query is even processed. So under extreme traffic, those direct connections are going to fail. If 200 application workers open direct connections, that's 200 database connections. That leads to massive memory consumption and absolutely crippling context switching overhead. The solution here is connection pooling. I like to think of middleware like PG Bouncer as a literal bouncer at a crowded club. By placing this transactional proxy layer between your app and the database, those same 200 app workers can securely share a pre-established pool of maybe just 20 to 50 actual database connections. This entirely prevents thread exhaustion and guarantees low latency, even when you're getting hammered by massive traffic spikes.
To bring this all together, here are 3 highly actionable system configurations you can implement to ensure maximum efficiency. First, right-size your max_connections. The default is usually 100, but pushing it beyond 200 or 300 will actually decrease your performance because of lock intention. Second, always enable the pg_stat_statements extension. You need actual data to monitor and identify your slow queries. And third, if your database is running on fast SSD storage, be sure to change the random_page_cost parameter from its default of 4.0 down to 1.1. This makes sure the query planner correctly values your high-speed index scans.
Well, we've covered the complete pipeline today, from the granular, row-level logic of analytical window functions and declarative recursive CTEs, all the way to the raw processing speed of composite indexing and keyset pagination, right up to system-level connection pooling. These concepts really do form the absolute foundation of high-performance SQL. So the final question I want to leave you with today is this. Is your database architecture truly ready to scale gracefully to millions of rows and thousands of concurrent users? Take these tools, dive into your execution plans, and find out. Thanks for joining me on this explainer, and I'll catch you in the next one.